Hey guys, welcome back. We're going to get into the Burger King menu in more depth today. So if you look at today's assignment, you'll see, I believe there's 31 menu items from Burger King, and with each one of them, we've recorded the protein and the fat. So we've got the two variables there. Naturally, when we have two variables, we graph them out. So we have our protein and our fat over here. So you want to observe the association that's between the protein and the fat, between those two. So anyway, that's a scatter plot. Let me pull up my calculator. I put it all in the list for us here. So there are 31 of them all together. You can see that. These are the z-scores, and those are the products of the z-scores, by the way. But we'll calculate those in a little bit so you can see that. First thing we want to do in order to visualize the association to see if it's a linear, really, is to look at, so we're going to do list 1 to list 2. So our X list going along the bottom is going to be the protein. We want to see how does protein affect the fat content. So list 2 would be our Y list. And we go to zoom 9. All right, so there's our scatter plot. It's the exact same thing you see here, except it looks better over here. The other thing is, if we want to find out what are the summary stats, which we're going to use mean and standard deviation. I guess I went ahead and gave you the correlation there. But to find that information, we just go to stat, calculate, and the second option, which is two variable statistics. We're doing list 1, list 2. There's no frequency list. Just hit calculate. So the X bar is a 17.2. I rounded. The S of X, a standard deviation for the protein, would be 14.0. And then there's 31 in this data set. That's what the N is equal to. And then on the other side over here, where we're talking about the fat content, the average fat content would be this Y bar. The S sub Y is a standard deviation for the fat content. Notice there is no correlation coefficient between the two. The way we calculate correlation coefficient is we actually run a linear regression. So I'm going to do the fourth option here, linear regression between list 1 and list 2. We can actually store the regression equation if we go to the variable option, arrow over to Y variables, function Y1. That's very important. So we're storing the regression equation as our Y1. Then we hit calculate. Now that will give us our correlation of 0.83, and then Y is equal to that. If we look here, that's going to be our equation. Of course, we will not use all that precision, but the calculator does it, so no big deal. And then if we hit graph, it'll actually graph our linear equation with our scatter plot there. So wow, that was pretty much the shorthand version of everything that we're doing. How the calculator does it for you. Then I guess the other thing that you might want to see is how we would evaluate that. So now that we have our model, that's not what I'm trying to do. All right, so now that we have our model, which was Y1, let's say that we wanted to know, what was the question yesterday? I think it was 25. So let's say you needed 25 grams of protein, and what would we expect for the amount of fat content? Well, according to our model, we can figure that out by going to variables, Y variables, function Y1, and then we're going to do an open parentheses to evaluate our model for an X value of 25. You can close the parentheses if you want, but it's not that important. And that would give you from the model the predicted fat content that would be associated with a protein content of 35 grams. Okay, so then the only other thing that we could talk about would be the residuals, but we'll get into that on one of the other slides. So anyway, that was really impressive because we were able to kind of review all that stuff, at least how the calculator does it and how to get it in the calculator in the first 3 minutes or 3.5 minutes. So lovely, well done. All right, so let's get into a little bit more of the theory we talked about yesterday. I just want to go a little bit slower today. I know you hate that idea of going slower, but I want to get into it, I guess, in more depth here. So first thing is that we always, whenever we're building that linear regression, that model that we saw here, it's always going to go through the mean point. So if I hit trace and I arrow up, my mean, the average for the protein was 14. So if I go to an average protein of 14 here, that would give me an association. Actually, let me evaluate that. That would be even better, because it should be this point right here, which is 14, and then the standard deviation about 16.5. So let me just go ahead and evaluate that. That makes more sense. So evaluate this for the point at 14, which is the mean, which should give us a standard deviation for Y. Something's going on here. Is it possible the data is different? Oh, I'm so sorry. Yeah, I was using the standard deviations. I should have used the means up here. Yeah, so the mean is actually going to be 17.2. Okay, so they give me a standard deviation of 23.5. Yeah, so that's the mean point. And regardless of what your slope is, you're always going to go through this mean point. So when we have typical or average protein, I said that backwards, when we have average protein or typical protein, then we would expect to have average or typical fat content as well. Okay, then the next question we have is how do we find the slope? Well, the way the slope is calculated is actually from the correlation coefficient. So we standardize the stat plot. We standardize it by getting z-scores. Remember, we calculate z-scores by dividing by their standard deviations. So for all this protein, we're going to divide all these or scale them. We're multiplying it by well, really dividing it by 14, and that will give us our standard deviation. We also are shifting it by subtracting it all from the average value of x. So there's a little shifting going on, and then there's the scaling. Same thing with to get z-scores here, we take all the values for the fat content, subtract it from the y bar, the average fat content, then we divide it by the standard deviation. That's how we're able to compare apples to oranges, because we can convert them to z-scores, right? So even though this one has a smaller standard deviation, this one's bigger. Whenever we divide them by those standard deviations, now we can compare z-scores across the board because they've been standardized by dividing. So what's happening here when we calculate the correlation coefficient, so we're going to take the sum of the products of the z-scores. All these green dots that are in the first and third quadrant are going to mean that we have a positive association, and then the red ones are going to negate some of those green ones because they're going to be negative, and then the blue ones that are on the axes, which have a z-score of 0, which is either average protein content or average fat content, they're going to lower the strength of the association but not change the direction of the association, which is kind of cool. So anyway, when we take the sum of all those products, we end up getting 0. The way that I did this, which the calculator of course does it for you, is I put in for list 3, I did the observation minus the mean divided by a standard deviation. I've shown that in a separate video, so I'm not going to get through it again. It takes a while. I'm trying to go fast. So same thing for the z-scores for the fat contents, which are all these. And then for list 5, I guess I can show you that part because it's pretty easy. I'm going to clear out this list here. Okay. And then I'm going to do list 3. So list 3 times list 4. Then hit enter, and those are the products of the z-scores. Then the only thing I have left to do is take the sum of list 5, which is the sum of the products of the z-scores. That's not what I wanted. Which I think I've actually already done that up here. Yeah, sum of list 5. Let me actually show you how you find that, though. It's probably what you really want to know. Anyway, so that's found in the list menu. So second list, arrow over to math, and then the 5th option down here is the sum, and we're going to do the sum of list 5. So that's second 5, then hit enter. All right, so that's the sum of the products of the z-scores, which you can see in the table. Then we divide it by n minus 1, which would be 31 minus 1, which is 30. So take that value and divide it by 30, which will give you the z-score. Or sorry, not the z-score, the correlation coefficient, which is 0.83. Now the correlation coefficient is going to be the slope of the standardized stat plot here for the line of best fit for the standardized stat plot, which is really brilliant and elegantly found and amazing. Then the only question we have now is how do we go back to the real unit dimensions? Because remember, we divided by the standard deviations and shifted, of course, in order to find the slope for the correlation coefficient. But how do we go back to real world units? So for every additional gram of protein that I have in a Burger King menu item, how many additional grams of fat would I expect to go along with it? So in order to go back to that, we just simply have to multiply it by our standard deviations. So anyway, z-scores are calculated observation by mean divided by standard deviation. This whole division of the standard deviation is what standardizes the whole thing in the first place. And then what we want to do when we go back is to multiply it by those standard deviations. So we have our slope of the z-score, which is our correlation, and then we want to multiply it by the standard deviation of y divided by the standard deviation of x, which is like our rise over our run. So if we re-multiply it by the standard deviation, that goes back to the real world units, the original units, and that's how we find our slope. So for our model, we use the hat over the top to symbolize it's a model. That's our predicted value. So the predicted y, which would be our fat content, is going to be equal to basically the y-intercept plus the slope times x. Also, sometimes this is done backwards where the x is here, like mx plus b format. It doesn't matter how you do it. So let's go ahead and calculate the slope. So to do that, we're going to take so here's our formula for that. We have our correlation coefficient, which is 0.83, times the standard deviation of y. So that's going to be 0.83 times standard deviation of y, which is 16.4, divided by our standard deviation of x, which is 14 grams. And then we can put that in the calculator. When we do that, if I hit alpha x, it'll let me put it in as a fraction, which is nice. It's the whole clear view part, or clear entry. All right, then we divide that by 14, and that gives us our slope, which that should look pretty familiar. If we go back to the y equals plot, that's actually our slope right there times the x, and then the other part over here is going to be our y-intercept, in case you're curious. So anyway, we've got our slope now, which is nice. And then to get the y-intercept, all we have to do is just kind of change around our formula. So we have for our model, the y hat, which is our predicted amount of fat content, is equal to the y-intercept plus our slope times x. Well, we already know our slope because that's going to be this value right here. So what we're going to end up doing is manipulating this by subtracting the slope times our x term on both sides, leaving us with the b naught is equal to the y minus the b1 times the x. Now this is actually being evaluated at the mean point, so we have to evaluate at a point. The only point that we know for certain is the 0, 0 for the z-scores, which is going to be the mean point here, right? Which is going to be the 0.7 or 17.2 and the 23.5. So we evaluate those points, and I'll put that in the calculator and we'll see what we get. Now, whenever I do this, it's going to be slightly off because the values are rounded. So the 23.5 minus the slope, which is what we calculate up there, even that's going to be slightly off because those values were rounded as well, multiplied by the average for the x, which is 17.2. So this is going to be slightly off of what the actual one is, which is calculated by the linear regression. So it's going to be, I think, 6.8. So the way that I could fix this is actually by using the averages from, so when I ran the two variable stats here, I don't need to store, well, it doesn't run a regression. You'll see the actual value for x bar is 17.1935 instead of 17.2. And then for the y bar, it's the 23.53. So you can actually, those values are stored. If we go to variables and we go over, variables down to 5, this is going to be a list of all the variables that we have that was run from our two variable stats. So if I want to do y bar, that's going to be the fifth option. And then I'm going to subtract from that the slope, which I'm just going to use this slope that I had up here, even though I know it's off by a little bit, but that's okay. And then times the x bar, so go to variables again, the fifth option for stats, and the second option for the x bar, and boom, now we got the 6.8. So 6.815, if we go up in here, 6.83. Okay, so it is still slightly off, but you know where our error is. It's going to be right here. The correlation coefficient was rounded, and these values were rounded as well. So we could do it exactly, but I'm really chasing after something that's not that important at this point. So anyway, moving on. So if we plug in those values, so here's our y-intercept and here's our slope, that'll give you the equation. I'll probably have you calculate these out by hand. I'll give you the equations, but most of the time we're just putting this stuff in the calculator. And whenever we store the regression equation, it'll give that to you as well. You already have there. So our model is going to be that the predicted value of fat, which is going to be this color here, our model is going to be the predicted value of fat is given by this y-intercept, which is what we would expect if we had no protein. So even in an item with no protein, we would expect would have 6.78 grams of fat, and then there would be a slope for every gram of protein that was increased. We would expect the grams of fat to increase by 0.972. So that's what a slope means, interpreted in context. And then our data themselves are going to be these blue dots. So notice the model does not fit a data perfectly. It's just useful because it gives us an ability to interpolate between what other things we might expect. So if we had 50 grams, we might expect whatever the value we get there. So this point here for the chicken sandwich, which had 31 grams of protein and 22 grams of fat, it had less fat than we would expect, probably because it's chicken instead of beef. So it's going to be leaner in this case, depending on the type of chicken that they're using and stuff. So so the residual that we would do is we would subtract from what we got from the model. So the residual function is RAP, is residual is equal to the actual minus the predicted. So we would take the actual value of 22, we would subtract the predicted from it. So if we wanted to find out what the prediction was, we can actually evaluate the function there. So I'm going to go to variables, y variables function, y1. So I'm going to evaluate my function from 31 grams. So for 31 grams, I would expect it to have that much fat content, but it actually only had 22. So I'm going to subtract the, I'm sorry, so it's the actual minus predicted. So the actual was 22 minus second answer will give me that previous number in case you're curious. There we go. And that'll give me a residual of almost negative 15 grams. So it's about 15 grams off of what we would expect it to be. It's 15 grams or 14.9 grams less than what we expected. That's what a negative residual means. All right, so when we graph this, whenever we run a linear regression, it'll give you the residuals. So we want to always graph the residuals. So I'll show you that. So first we ran the linear regression, which is the fourth option. We've already stored the regression equation, so I'm not going to do it again. Whenever I do this, if we go to the list menu, so second stat to list menu, this bottom one's residuals. That'll be the residuals from the linear regression, the last linear regression we ran. So I'm going to graph my stat plot across the x-axis with the residuals across the y-axis. So I go to second stat and then the eighth option, which is the residuals, and then do zoom 9 again. Oh, this is funny. So this line here is going to be our model being graphed out. We don't need that anymore, and I think it's still going. That's kind of annoying. Oh no, you see the little wheel spinning in the top. All right, so if we go into our y equals plot, you'll see that it had the model turned on. So we can turn that off by just arrowing over it and hitting enter. Now whenever I select graph, it'll graph the scatter plot without that y equals our model being shown, which is fine. Now when we graph this out, we see no clear pattern. It's pretty random. It's the exact same information we have here. So we're graphing the protein and the residuals across that, and that's essentially what's going on. This line here, that represents our model. So instead of it being like at a slope, it's going horizontal now. And the points above it are going to be what was higher than expected, and the negative residuals are like the chicken, which I think would be like that point right there, or it's that one, I don't remember, which would be less than expected. Okay. Anytime we have a curved pattern, that means that we were actually fitting a linear model to curved data, and so it went down and it went back up, right? And if we have unequal, so if we don't have a pattern, it's random, that's good. That means that it was linear and you're good to go. Don't worry about the actual spread about that, because they will, when you're doing the zoom stat, even if there's hardly any spread, they're still going to like zoom in on the residuals. It'll just be these numbers will be smaller. Okay, so don't worry about the spread unless there's unequal vertical spread. So see how it starts out really rough, then it gets more accurate. It's called a fan pattern. Usually fan patterns start out accurate and close, and it's the reverse of this. Then it fans out, so the model is good for smaller values, but as we get further out, the model becomes less accurate. So this is, you got to be careful for that. Outliers like this one point up here, that means that it's probably actually drawing the entire model high, and it's probably throwing off the model. So if we could remove this outlier, as long as we tell people what we're doing, but if we remove this outlier, we would get a better model, and we could actually explain more of the variation in the y variable with the x variable with our model. So anyway, make sure it's not curved. That's the big issue, because then it means that it's not linear. Make sure you have equal vertical spread and you don't have any outliers. All right, so we'll do a little regression to the mean. So suppose that we have a new student. We wanted to guess his ACT score. Where would we start? Well, if we know nothing else about him, we would just assume that he was typical or average, or the most likely outcome is that he has an average ACT score. So that's where we would start. All right, so suppose we have a new student and his shoe size is 1 standard deviation above the mean. How does this affect our guess? Well, the correlation between shoe size and ACT is 0. So that slope of the standardized stat plot is 0, right? We're not allowed to increase or decrease at all. So that's just going to be 0. So even though we know that he's 1 standard deviation above average for the shoe size, that's not allowing us to increase or decrease or deviate at all from the mean for the ACT score. So our prediction for the y, even though our prediction of the x, the shoe size is 1 standard deviation above, we're not allowed to allow that to increase, or if it was negative, decrease our estimate for the shoe size or for his ACT score. So we're stuck at just guessing the mean. We're no better off than when we started when we didn't have any information, because the correlation was 0. They're not associated with each other. All right, so at least not linearly. All right, so we plug it in. So we do correlation of 0 times 1, which is just going to be 0. So our predicted value, the z-score for y, is just going to be 0. All right, now we know his GPA is 3.9, which is a z-score of 1.8. How does that affect our guess? Well, what's the association between GPA and ACT score? Well, those are pretty moderately associated. So students with higher GPAs tend to have higher ACT scores. So this allows us to have a slope of the standardized stat plot of 0.6. So if I go over 1.8 standard deviations among the GPA, that allows me to go about to 1. We'll see. So 1.8 standard deviations for the GPA here. So we're going to multiply 0.6 times the 1.8, which is going to be 1.01. So that allows us to deviate in the same direction, because it's a positive association, to about 1.08. So it's really like, it's how strong the association is allows us to pull with that amount or that portional amount to predict values that far away from the mean. Okay. Now the y prediction for the y will always be less than the actual value we had for the x, unless we have a correlation of 1, which rarely ever happens. Anyway, that's called regression to the mean, essentially. All right, now we know his SAT score. So the ACT and SAT, they're pretty well related. So if his SAT was two standard deviations above the mean, so that would be here. So SAT score was over 2 standard deviations. Now the correlation between these two is 0.9. So notice that that has a steeper slope than the 0.6 and a steeper slope than 0, right? So now it allows us to deviate in the y direction even more. So 0.9 times that 2 is going to give us the 1.8, which means it'll allow us to estimate that he has an ACT score. We can go comfortably go 1.8 standard deviations from the mean. The reason we were so comfortable in doing that is because there's such a strong association between those two. When we didn't have as strong of association, there was more of a gap between there, okay, at least in proportion. All right, so we're going to do example 2 real quick. Now, the first thing we need to do is input this data here. You do not have to do all the Burger King data, because that's a lot, but I am going to put this data in here, and I need you to do it as well for this example. This will be kind of what you'll be expected to do on a quiz or a test or something like that. So one thing I'm going to do is I'll pause the video so that I'm going to clear all my entries, clear all list. Okay. And then I'll pause the video and I'll continue whenever I have all this in. So, all right, so now that I have it in the calculator, I want to go ahead and graph the scatter plot. It's always the first thing we do. So we graph it out. I'm going to do list 1 to list 2 because we're graphing, let me see. Actually, here's the data for a set of BMX bikes showing their weight and maximum number of inches the rider was able to get. So we want to see, how does weight determine the height that they're able to get. So yeah, we are doing list 1 to list 2. So make sure you have your X and your Y list correctly. Then we'll do zoom 9. Okay, so this is a negative association, right? Pretty well looks like it's in line here, so no real issues there. So as we increase the weight, we would expect, as of course, that the height of the trick is going to go down. Does it meet our condition? It's linear, yes. We don't have any outliers. These are deviating a little bit, but it's not an outlier. And the data is quantitative, so we're good. Sketch your scatter plot, you can just put that down pretty quick. It says first, create a model used to predict the maximum height of a trick of a BMX bike weighing 24 pounds. So predicting the height from the weight. So we want to make a model. So we're going to run a linear regression, calculate the fourth option for linear regression. And we're going from the weight to the height. So that's going to be list 1 to list 2. So list 1 to list 2. I'm going to store the regression equation. I'm going to store it as y1. So go to variables, arrow over to y variables, function y1, and then hit calculate. So we have a very strong correlation as we expected. We can explain 97.6 of the variation in the heights of the tricks based on the weight of the bike, which is incredible. Then you have your slope, which is negative. I'll go ahead and put that here when we're making our model. So anyway, there's your slope. I guess I'll pull it up here. And then B would be your y-intercept. So this is basically your model, except we're going to define the y and the x in context. So it's height with the hat on the top of it. So the predicted height is equal to our slope times the weight of the bike plus the y-intercept. All right, use the model to evaluate. We want to find out what we would predict for a 24-pound bike. So we can quit out of this menu here, or I guess just arrow down would be just fine. And then we want to use the model that we had. So y variables function y1, and we're going to evaluate it at 24. which will be basically 9.6. But if we look here, 24 is higher than our domain. So there is no weights that were over 23.5. So this would be technically extrapolation. Now it's not that far out of extrapolation, but still we shouldn't trust it necessarily. Now we want to create a model to use it to predict the weight of a bike that had a maximum height of a trick of 12. Now, again, we don't have any values of 12 here, so this is going to be lighter than 19, and again, extrapolation. But notice now we're predicting the weight from the height, so we need to create a new model. This time we're going to reverse our variables. So now we're going to do list 2 to list 1. Okay, I'm going to store the regression equation as y2, so variables function 2 for y2. Then hit calculate. Okay, so we can write down the slope and everything for our equation. No big deal. Now we want to evaluate that for a 12-inch trick. So we're going to go to variables, y variables function. We're using our second model now, and we're going to evaluate that at 12, which will give us 8.89. So again, that's extrapolating because we didn't have anything that small. So there, and that might not even be possible to have a bike like that, right? So anyway, discuss your confidence using these models for the predictions. They're extrapolation, so we wouldn't actually trust them. It's not appropriate. We can only use the models for value to predict values that lie within our domain or our range, depending on what direction we're going in. All right, number 3, is there a positive association? It says, sorry, there is a positive association between a number of private music lessons a student takes and their family income. So describe what this means in a language a 10-year-old would understand, which is like slope. Okay, so what that means is so the more a family income, the wealthier a family is, the more the family income, then the more number of private lessons they can afford. That would be the general association we're seeing, or we would say there's an association between or families with larger incomes tend to have more private music lessons, okay, because we actually aren't assuming the direction of that in that way. All right, does this mean that taking private lessons will increase family income? So we don't know which way it goes. Is it that private lessons increase family income, or does family income increase private lessons, even though that one kind of makes more sense? But we can't state that without a carefully designed experiment with randomly assigned treatment groups. So instead, correlation is not equal to causation. We cannot conclude that without a carefully designed experiment. All right, so we have to know, are the statements true or false? If false, explain briefly. So some of the residuals from a least squares linear model will be positive and some will be negative. Yes, that is true. So unless there's a correlation of 1 and it's perfect, you're going to have some that are high and some of them will be low. Least squares means that the sum of the squares of the residuals are minimized. Okay, sorry, some of them are minimized. This is actually incorrect. So this is not some of them are minimized, but all of them are actually minimized. It's not showing that. Yes. Okay, so if we change the word to the sum of the squares of the residuals are minimized, then it would be true. That was what I showed you guys yesterday. All right, so we write y hat to denote the predicted values and y to denote the observed values. Yes, the hat tells us it's a prediction from the model, and the y tells us that it's an actual value from the data, and we should trust it more. All right, so that's it. I hope you guys have a good day. If you have any questions, you can join me on the Google Meet at 1 o'clock. See you guys later.